Okay, welcome back. Now we're getting ready to talk about hydrogen bonds. Um, Hydrogen bonds, of course, you know that they are involving hydrogen. Uh, that's key. Number two, hydrogen bonds are created between molecules, okay? When we did the covalent bond, that was between atoms, or when we did the ionic bond, that was between atoms. But now we are talking about hydrogen bonds, and they occur between molecules, okay? And they occur between molecules when there's a strong attraction taking place. Now, how do we get that attraction? So one of the things that we know is that we first have to have um, polar molecules, because we have one molecule attracting another molecule. If you remember, just like when we looked at water, water had an end of the molecule that was more negative than the other end, which was more positive. Okay, so water, we said, was a polar molecule, and one polar molecule can attract another polar molecule. So since we're talking about hydrogen bonds, we want to say this is going to occur between molecules where hydrogen has to be in a covalent bond with one of those electronegative guys, because we know that things that are more electronegative cause this charge destabilization across the molecule. So if hydrogen is in a covalent bond with an electronegative atom, such as fluorine, oxygen, nitrogen, chlorine, those are some examples. We know that the electrons are going to be drawn further away from hydrogen, making that end of the molecule partially positive, and the end where the electrons are being drawn partially negative. Okay, so it says it involves the sharing of that hydrogen and its electron between two or more atoms. Okay, so let's see if we can put a water molecule on here without these other things taking place. I saw that. I'm just going to pretend I didn't see it. So we've got this partially positive end of the water molecule. We got the partially negative end. Okay, so we know if we had another water molecule, and I drew that closer than I really wanted to, we know that this guy is going to hydrogen bond. If you can see those, and then this can hydrogen bond there, okay? But this oxygen can hydrogen bond to that hydrogen, okay? So hydrogen bonds are more easily broken than covalent bonds. We said that hydrogen bonds are represented by a broken line. So they're represented by a broken line. However, when we get many of these hydrogen bonds in place, we know that it's going to help to bring some structure and function, and it makes things quite strong. So say, for instance, if we were looking at, we said it helps to maintain structure and function in cells. So let's just say, for instance, we were looking at a double helix. Well, what's holding that guy together are the hydrogen bonds that are occurring between the bases. So adenine, for example, paired to thymine, cytosine connected to guanine. Okay, so hydrogen bonds, we said, even though they're weaker than a covalent bond, because remember this is a covalent bond, it says, but when we get many of them together, they become quite strong, and they can help to maintain structure. Say, for instance, if we were also looking at a helix, okay, in protein structure. So here are the hydrogen bonds that are going to hold that secondary structure in place, whether we're talking about a helix or a beta sheet. Okay, so let's move forward and show you some examples. So here's water. And then here's ammonia. Okay, so here's the nitrogen. Okay, and we know that this is the oxygen. Oh, because it's red. Here are the hydrogens. But anyway, the hydrogen is partially positive, the nitrogen is partially negative, and here your bond that's taking place, your broken line that's taking place. So there's your dotted line. Here again are water molecules. Okay. So if you had two water molecules side by side, we know that they would rearrange and orient themselves with the oxygen being drawn towards the hydrogen. All right, so let's move on to the difference between an empirical formula and a structural one. Which one would you say is, I guess, the better representation? Well, that depends on what you're looking for. So let's talk about the empirical formula. Well, if you just saw on the last slide, the empirical formula basically makes books lighter. So it's more concise. It tells you the exact number of what element or atom is in a molecule. So we know it's used to save space. H2O tells us that we've got two hydrogens and one oxygen. So that would be H2O. Okay, so when we last left off, we said that the empirical formula was most concise. We said use to save space, always tells us what the components are. Now let's go on to the structural formula. The structural formula is, we know, more accurate because it's going to tell us the exact arrangement of each of the atoms in whatever the molecule is. Now, one of the things that we want to look at now are isomers. And the reason we want to look at isomers is because isomers will have the same empirical formula, but the structural formula is going to be different. They're going to have molecules with the same empirical formula, but the structural molecule is going to be different, or the structural arrangement will be different. Now, so what we want to look at is C2H6O, which makes two chemicals depending on the arrangement that we want to look at, and that is ethyl alcohol and dimethyl ether. Again, the formula for those are, we said C2H6O. So depending on the arrangement is whether we'll get ethyl alcohol or whether we'll get dimethyl ether. Now, one of the things that we said is the reason why structural formulas are important is because these may have very different properties. We know ethyl alcohol or ethanol is liquid, and we know that dimethyl ether is a gas, and only under pressure will it be found in the form of a liquid. Okay, so again, they may have very different properties. Dimethyl ether, you definitely never want to have that inside. Ethanol, you don't really want that inside either, but dimethyl ether, you never want to have this chemical inside. Again, different properties. We know that ethanol affects kidney, liver, maybe the central nervous system, can do damage, can be lethal. Dimethyl ether, definitely target organ is your central nervous system. Okay, but anyway, let's move on and just take a look at these guys. And the reason why we're mentioning isomers, because when we get to chapter 3, we're going to look at isomers of glucose, for example. And then we just want you to know what an isomer is. So again, there's that formula C2H6NO. Alright, so here are the two isomers. In yellow, those are the hydrogens. The red is the oxygen, and the black is the carbon. Okay, so what we're going to find out when we get to chapter 3, this hydroxyl group always makes alcohol, sugars, and then this is di. We know that means 2 methyl, so we're going to have 2 methyl groups. So a CH3 is a methyl group, and a CH3 is a methyl group. Alright, so that's just showing you, once we arrange them structurally, two different totally different things. Now, let's talk about the biologically important molecules, and we're going to classify them as biologically important molecules, but then we're going to further classify the last 4 as biologically important molecules, but they're also considered to be macromolecules, and the macromolecules are the ones that we're going to talk about when we get to chapter 3. Alright, so water, biologically important molecule. In a minute, we're going to talk about some of the characteristics of water. And then, remember I said we're going to talk about the biologically important macromolecules when we get to chapter 3. But we're going to go ahead and mention them here because they are important. Carbohydrates, so the carbohydrates, the fats, slash lipids, the proteins, and then your nucleic acids. So these are biologically important molecules. So let's look at water first. Water, we know, is very important, and the way that we want to I guess the characteristic of water that we want to talk about first is that water is a universal solvent, and we know that universal solvent means that it is able to dissolve just about anything. Okay? And that ability to dissolve just about anything comes from the fact that water is a polar molecule. If you remember the oxygens, say for instance, we wanted to put salt into solution. The oxygens would surround the sodium and push it away from the chlorine, and the chlorine will be surrounded by the hydrogen. So it's a universal solvent, can dissolve just about anything. We know the one thing that it cannot dissolve is what? Think about it when you're cooking. Absolutely. Fats, oils, okay? The only thing they do, I don't care how hard you shake them, they float to the top of the water. Okay? And water also has a high specific heat. Okay? So we know that with water, though you don't have drastic temperature changes, and that the not having drastic temperature changes has to do with those numbers of hydrogen bonds. So the temperature of water, I don't care if you put it on a hot stove in the pot, it's not going to quickly evaporate. Okay, that water has to slowly rise up to boiling, and then you'll eventually see the steam rising off. So temperature rises slowly, it also rises slowly, and it also falls slowly. If you have a glass of water that you place in the fridge, it doesn't immediately freeze. It's going to take a minute for that, or a few minutes for that water to actually freeze, so it falls slowly as well. And we know that this is important because it's going to protect organisms from rapid temperature changes. Excuse me. All right. Next one, and again we said high specific has to do with hydrogen bonding. It being a universal solvent has to do with hydrogen bonding. Water is also very adhesive and cohesive. Adhesive, meaning that it can stick to other surfaces because of what? Its polarity. Positive charges will attract the negative charges of some other surface. Water is also cohesive. The hydrogen bonds holding it together. So when you get up in the morning, you turn your faucet on, not just one water molecule pops out, but it flows out. So this creates a great delivery system because of all the nutrients that are present that need to be delivered to all the different cells. Water makes a great delivery system, okay? Next, water has a high surface tension because of what? Is it polarity or hydrogen bonding? You guessed it correctly. Hydrogen bonding, okay? Because water has a high surface tension, you can go out there, you can float a boat on the water, you can ski across the water, you can skip a rock across the surface of the water due to all of the hydrogen bonds, okay? Another example or another characteristic is the fact that water is more dense as a liquid than it is as a solid. It's more dense as a liquid than it is as a solid. If you look in your books, probably on page 29, they show you a water droplet versus water that has been crystallized. And water that is liquid has lots of hydrogen bond, is tightly packed together. Water that is frozen has opened up into this hexagonal structure, and it is